Carlos Ramirez here for another fun and interesting physics problem. Today we'll be doing number 70 in chapter 7. Now I'm going to read you some background information for solving the questions that are going to be asked. A sled with a mass of 5.80 kilograms is pulled along the ground through a displacement given by d equals 4.55 meters in the x direction. Letter A in this 3-question problem reads, how much work is done on the sled when the force acting on it is 2.89 newtons in the x direction and 0.131 newtons in the y direction? Let's go ahead and write this information down so we could review it a little bit more. We have our mass, 5.80 kilograms, and our displacement, which is 4.55 meters, and in the x direction. The force itself is 2.89 newtons in the x direction and 0.131 newtons in the y direction. Now the force is already split into the x and y components, therefore theta, sine, and cosine are useless. As I had mentioned earlier, the problem states that the sled is being pulled along the ground. This is inside knowledge as to the sled is moving strictly horizontally. Therefore, the y components cancel out each other or reach equilibrium, which is the same as cancel out each other. On the next slide, let's go draw the free body diagram. You have the dots represent the sled, gravity, represented by mass times gravity, acceleration, the normal force, and then we know that the force has both a y and an x component. So we draw a dotted line now to represent the x-axis. I draw our force over here, and we see that it has a y, also an x. Let's do our total sums of the x and y directions on the next slide. Sigma force in the y direction. As I mentioned, that it is not moving vertically, therefore it cancels out each other. We have our gravity subtracted by our normal force, subtracted again by the y component of our force. Now this will equal 0. We could move it around and realize that gravity equals the normal force plus the force in the y direction, and this is apparent as you can see that the normal force plus the force in the y direction cancel out against the gravity down here. Therefore it's strictly moving horizontally, not vertically. The total sum of forces in the x direction is simply the x component of the force, as is the only thing moving horizontally. And as we know, work is parallel to the displacement. Now we have our formula for work, which equals force dotted into the displacement. Now these two are both vectors. The magnitude of both vectors are being multiplied together, and this creates a scalar magnitude, which is that of work. We have the x component of force, so it is simply force, the x component dotted into the displacement, and let's go right numerical values. 2.89 newtons. Again in the x direction, and this is going to be multiplied by the displacement, which is 4.55 meters, also in the x direction, as they work and displacement are parallel to each other. Must be, or else, oh, that's the only way to have a value for work. And when we multiply these two values together, we get one for work in general, and it is 13.1 joules. Joules is the unit to represent work, and this solves letter A. Letter B is very similar, eerily similar to letter A, the only difference being that the y component has changed. Let me go read it for you. How much work is done on the sled when the force acting on it is F equals 2.89 newtons in the x direction, which is the same value we had in A, but this is where the difference comes in. 0.231 newtons in the y direction. So we can go write down our new force. This is B. 2.89 newtons. The x. We have our new y. But as we will soon see, a change in y will not make a change in the amount of work. No, as you have seen. The sled is still moving horizontally and has not taken flight. So let's go draw another free body diagram just for visual learners. The gravity, normal force, has not changed. The y component is greater here. Since there is no change, we have the original force in the x, then we have the displacement, which again they do have to be parallel, and the same answer that was in letter A is apparent in letter B. Now on to the third and final part of this problem, letter C. It's more of a conceptual problem. It reads, if the mass of the sled is increased, does the work done by the forces in parts A and B increase, decrease, or stay the same? Since this is strictly conceptual, there is no numerical values needed to answer this question. Now we know that force does equal mass times acceleration, and the formula for work is force dotted into displacement. So as you can see, mass does directly play a part. Since the mass is multiplied directly to the constant that is acceleration, it's retreating itself, the x and y components that we had previously gotten are subject to change along with the increase of mass. A greater figure for the force will calculate to a larger value for the work when multiplied against the displacement. For demonstration purposes, let's come out with some values of our own. If we were to say that mass is equal to 5 kilograms and acceleration is equal to 10 meters per second squared. Again, these are purely numbers that we have come up with to prove the conceptual. We have a force of 50 newtons. This we get from using the force equals ma. Now, when we plug this into, let's go to the next slide, the work formula, dotted into displacement, we have 50 newtons multiplied by that of another value that we can come up with, 2 meters. We will get work, in this case, is 100 joules. Now if we were to increase the mass here, and let's call it 10 kilograms now, you can see that multiplying 10 by 10 you're going to get 100, and so the work needed, or the work done, is going to increase as the mass increases, as this is directly proportional thanks to this formula right here. And with 100 newtons multiplied by 2 meters, this is if the mass is increased, you're going to get a larger value of 200 joules for your work. This proves that with increased mass, there is an increase in work. I have shown you letters A, B, and C of question 70, and this is the end. Thank you for watching. Stay tuned for another whiteboard presentation by Carlos Ramirez.